Thank you for joining us for a very brief presentation of the RESET Index. For those who aren't familiar with RESET, it is a standard for measuring the performance of indoor spaces in continuous time. With respect to air quality, the standard requires monitors within mechanical systems for building owners and within indoor spaces for tenants. The standard is used around the world across a variety of project types. At the core of RESET is a standard for data, where we look at the elements that affect data quality, primarily monitor accuracy, location of installation, and maintenance. Now, onto the topic of the moment, estimating and controlling transmission from aerosols. Let's first acknowledge that the range of advice surrounding this topic is highly confusing and often contradictory. All of it is right and all of it is wrong. Why? Because air quality is constantly changing and needs differ from situation to situation. As a result, a complete approach to modeling infection risk from aerosols needs two complementary parts, a predictive design tool and a responsive operational tool, with the latter being our focus. In order to achieve this, our approach has been to use scientific literature that can be applied to operational building science and map each variable to sensor data, yielding a standardized real-time score. More specifically, our approach has broken infection potential into virus health, immune system health, and dosage. To serve as an example, we'll use virus survivability and immune system health as variables, while keeping dosage constant and expressed as a factor of 1. The following slide shows the impact of humidity on the survival of the influenza virus from 3 well-known cornerstone studies. As we can see, their conclusions are all quite different. Overlaying the results yields the following graph with an average 28.8% uncertainty. Repeating the same exercise for the impact of humidity on the human immune system yields the following result. In turn, overlaying these two results gives us the following estimated infection potential, which we then overlay with research on actual infection rates from another cornerstone study. The final result shows that the trends tracks closely, with the key difference being the acuteness of the peaks and troughs. Now, turning our attention back to dosage for a moment, this variable is most commonly tracked by using CO2 as a proxy for virus particles being emitted. In this way, basic data from RESET accredited sensors deployed using a standardized method can be used to model 3 complementary indices. The Building Optimization Index considers the optimization of building systems in real time. The aerosol infection potential is slightly different in that several of the parameters are computed on a rolling average, seeing as their health impact comes from exposure over time. The Certainty Index follows the RESET ethos of transparency in the accuracy of data being communicated. Of course, real-time modeling becomes a whole lot more interesting when more real-time data is available, particularly as it relates to filtration, air cleaning rates, and particle size. Data such as fan speed and density and size of liquid aerosolized particles allow users to decouple CO2 data from calculations of risk. This further allows users to actually measure the efficacy of different filtration approaches, such as portables versus ceiling-mounted solutions. This is especially important as a maintenance tool over time, enabled with notifications when the certainty of human error starts to slip in. In the last minute or so, we've anonymized a case study that demonstrates the feedback loop created by real-time data. This first image represents an optimal office in a pre-COVID scenario, with an infection potential of 40% if all occupants are infected except for our person of study. In this figure, we turn on pandemic mode, consisting of 100% outdoor ventilation. Now, most buildings are not designed to heat, cool, and filter that much outdoor air. As a result, during winter, we find indoor temperature, humidity, and pollution levels that cripple the immune system and increase the survivability of many viruses. In this particular example, even though occupancy is down 50% and CO2 has dropped to 600 ppm, infection potential has only decreased slightly from 40 to 30%. Using the data for predictive purposes, in this case study, the operator notes that infection potential only approaches 0 when CO2 approaches 400 ppm, particles approach 0, and the air is heated and humidified to human comfort zone, necessitating enormous amounts of energy. This doesn't need to be the case. When working with data and empowering building systems to assess and respond in real time, we find that a blend of ventilation with central and hyperlocal filtration enables users to drive infection potential from aerosols down to an absolute minimum while keeping energy costs low. But the most important realization in working with real-time assessments is that air quality is ever-changing and that the blend of ventilation and filtration needs to as well. Ignoring this reality will require the industry to oversize systems and burn through a lot more energy to meet results.